One of the analysis tools in Cimatron is a very powerful function for motion analysis. Running a mechanism through a motion simulation is an ideal way to test the design and catch potential mistakes, like missing clearances or interference. A motion analysis is actually quite easy to set up too, as long as you understand the basic principle behind the function and follow a few simple rules. The first and probably most important thing to know about motion analysis is that it uses a true kinematic engine. The motion of the bodies is calculated by the force you enter and the contact with other bodies. This requires the system to run a series of complex calculations over a span of time, but it means that the result is the actual mechanical motion of your mechanism. If instead you only wanted a quick way to show some objects moving, you'd be better off using the assembly function move-rotate. Move-rotate has no calculation at all. It just allows you to drag parts in their free directions. This means, however, that it does not recognize steel-to-steel contact, so it should only be used for simple visual tests. The way to use motion analysis effectively is to stick to the basics. First-time users of this function usually overdefine the movement and then have trouble. On the screen is an 8-point checklist. These are the steps and the order in which to do them that will generally guide you through a quick and successful motion analysis. Some of these steps only take a second, but each one is noteworthy. Today, we will go through 4 motion analysis examples, and each time go through the checklist. If you're writing this down, I'll refer back to this list a few times as we go along. Let's start with a very common mechanical motion in mold design, a pin-driven slide. This is a good example of something that you might want to verify the motion on. The first rule on the checklist was about defining groups. But what is a group? Groups are something that can be made anytime from the dedicated Group tab on the tree. Under the heading of unassigned parts, you'll find the entire assembly tree repeated. But groups are entirely independent of the assembly tree. Any parts from any subassembly can be grouped together. Picking the parts on the screen and using the right mouse click in the group window will create a new group. Because the groups tree does have light bulbs, you could actually use these groups as another way to hide or show parts. But really, the reason groups exist is to facilitate the motion analysis. The light bulbs are handy though for getting already assigned parts out of the way, so that other parts can be more easily selected. Once a group exists, the right-click menu has a few more options on it. These are the obvious needs, like renaming a group, deleting a group, or attaching parts to an existing group. Now might be a good time to enter the motion analysis function. Here the groups take on a different look. The parts share a common color, but it really doesn't matter whether the groups are created while inside or outside of the motion function. FYI, in the modeling chapter of the preference area is a page that sets up the default group color pattern. But also the group colors can be set right in the motion analysis dialog that's opened up across the bottom of the screen. There is a lot to talk about in this dialog, but first I should finish up with rule number 1, which was to group the parts that move together. What I have so far is not correct. The Gibbs and wear plate do not move in relation to each other, but the slide part does, so it must belong to its own group. Any part that moves independently must belong to a separate group. Drag and drop is allowed in the groups tree, so that's another way you can use to attach parts. I also need to mention the orange buttons in the group tree. This is the toggle to ignore or consider the group during the motion calculation. These will usually be set to consider, but if you have many different groups and some are for different motion runs, you can toggle some to ignore. Rule 2 on the checklist was to use the fewest parts possible to define the motion. Because this function requires calculation, unnecessary parts will make it run slower. Yes, it will simulate motion on an entire mold design at once, but because I only want to prove out this slide, I really only need to contend with a few parts that are directly involved. Rule 3 states that one of the groups must be locked in place. Without a motionless group to push off from, the reactions of the other forces cannot really be determined. The push pin in the motion window is how to set this. It's a simple but important step that must not be overlooked. And next comes the actual definition of the motion direction. But really, it's better to use the word force. Define the input force acting on the design. Motion is really the result, or what will happen to the parts when they are acted on by the force. To define a force vector, double-click in a time cell that corresponds to the group that will be moving. Here, the B side needs to move down and away. The vector arrow is like any other arrow in Cimatron. There are numerous different ways to define its direction. And a distance must also be provided. In this case, 3 inches is enough to see if the slide works as intended. The second aspect of the force definition is the concept of time. The time grid allows other motions to be defined in a certain order. How long one motion lasts doesn't really matter, except that by default the system is set to run calculation every 1/10 of a second. So by making the motion over a larger period of time, you add more calculation steps and generally refine the accuracy of the analysis. Rule 5 suggests that you test the input force by running the motion in free mode. Free mode is a toggle to run motion without any calculation. So it's just a visual mode to make sure that the force you define is correct before you wait on the actual calculation. Rule 6 is in regards to open solids, and that takes me to the settings area. There are only a few settings to be aware of, but note that by default, non-closed solids are ignored in the motion calculation. That setting would be fine for this example and many others. But if the analysis is working on very complex blocks, they are often not perfectly closed, and you will need to have the motion consider the open bodies. Doing so requires a little more effort from the system, but the results should be fine. Note also that the time step setting is here. So rather than adding time in the input vector, you can also refine the calculation step by changing this value. Either option has the same effect of adjusting how many calculations take place over the movement distance. I'll set the dialog back to calculation mode. But before the actual motion kicks off, follow one more rule, interference check. Run a static interference check on the parts as they sit. If any of the bodies overlap, the design already has a problem that must be fixed. Here we find out very quickly that the parts have no interference and so are good to go. The motion calculation puts the force into action and the parts contact and react. If it finishes, that means the design had no collisions or binding over the distance traveled. A calculated motion can be played over and over, or the slide bar can be used to place the positions anywhere you might want. Dynamic section can be used at the same time as motion, which is a nice way to really check on how the parts are interacting. The measuring tool also works while using motion. So I can check on something like how far the slide has traveled given this pin length. So those are the basic steps to working with motion analysis. Now let's take this example a little farther because the slide sticks out past the gibs. So actually I left a few too many parts out of the equation. I need to include the plate with the slide pocket in it. The B plate moves with the gibs and the wear plate, so it doesn't need a new group. it can be added to the existing B-side group. With any change to the groups, the buttons for interference and calculation become live again. Again, the process completed successfully, but the result is going to illustrate how the forces working within the motion analysis can often react. It's best seen in side view. As the motion takes place, the slide moves back, and it does come into contact with the back of the pocket before the slide pin is free. Here, as the mold continues to open, the slide actually keeps moving to the left, and it drags the plate and the entire B-side group over with it. So despite the vector on the B-side group telling it to move downward, the forces of the objects interacting can still cause motion in a different direction. This is kinematics at work and is what the system will always strive to do. Move the parts in such a way so that the motion can finish. But to prevent this, what I should have done when I added the B plate to the analysis was to also add the A plate and the leader pins and bushings. This would have kept the mold plates in alignment just like in the real mold. Or I can enhance the groups I have now by adding some permanent connections. Permanent connections are basically extra instructions that you can apply to the simulation. The last run on the checklist states to use them only when necessary. That's because it's very easy to over-define the run with too many of them and just lock up the process. To define a permanent connection, select a face or point from each of the two groups where the extra rule is needed, then set the connection type. In this case, the need is to make sure the alignment in X is kept. So I can establish that the current distance between these two vertical faces is not allowed to change. With the permanent connection in place, now the result of the simulation ends in a collision, which is correct. Collision just means that the mechanism can no longer move even though the defined travel hasn't finished yet. A few good options help to highlight the exact area where the collision has occurred. It's clear to see that the slide contacts the back of the pocket before the pin is free, so this design is in error and would need to be fixed. Definitely a helpful motion analysis. Let's switch to a different example in order to discuss springs. The motion analysis tool can recognize coil or gas springs as an input force on the mechanism, but they have to be correctly defined. Prior to making a new simulation in the same assembly, the previous one should be saved with a specific name. Saved runs can be loaded again later, or a new run started. Starting a new simulation throws up a safety warning to make sure you understand that the previous timetable grid is going to be reset and cleared. So now I've got a clean motion grid and the checklist steps can be repeated all over again. Grouping is always the first task. Because I want this example to stand on its own, I'm actually going to make all new groups rather than add these parts to the existing A and B side groups I had from the previous run. For the purposes of motion analysis, springs have to be marked and then defined. Both options are found in the right-click menu from the Groups tree. If the springs were added from a catalog, they should already be marked. The system recognizes them as springs based on their attributes. But defining them is still important. The motion function only understands springs that push, not pull. So as the springs are designed compressed, the system wants to know the original spring length and the spring rate. Spring rate only comes into play when there are multiple sets of springs competing with each other, like in a three-plate mold. The stronger springs will work first until the free length is reached. If the groups are already defined, the spring should automatically understand the objects they are pushing on, but it's good to double check that. Like before, the A side group will be the locked group, and the input force will be the tool opening in Z. Don't create a force vector for the springs. The spring definition is all that's needed for the system to understand their purpose and the groups they push on. Because the first slide is still colliding, I want those components to be ignored. Remember, you can control which groups and parts are being calculated in the run by using the orange icon row in the groups tree. Again, the interference check gives a clear result, so I can go ahead and calculate this motion. In this example, as the heel block moves out of the way, the springs provide the force to move the slide backwards, up to the point of their free length. A nice touch is that the system visually stretches the springs, so they really look like they're pushing. Also note here, when you play the simulation backwards, it really just moves backwards. To get the true mechanical check of the mold closing back up would require an up vector be added to the simulation. Looking back at the motion analysis checklist, we see the only step that really took any time was the first one, correctly grouping the parts that move together. In both examples so far, only one input force vector was needed. And that's often true in more complex examples as well, because most of the motion is really from the mechanical design of the mechanism. Remember, you only apply the input force and then let the function do the work. I've got time for a few other examples, but in every case, I'll just be applying these same simple rules over and over again. The next example is also a common mold mechanism. It's an accelerated ejection system. Like before, the first step is to group the components. When simulating ejection in molds, you may also want to add the plastic part into motion, and that will work, although the parts can often be heavy and slow down calculation. In this case, the point is to simply verify the plate lifters, so I'm following the advice of step 2 and leaving the plastic part out. Most of this homemade tilting mechanism is stationary in the ejector system, even the dowel pins, but the lifters move on their own, so they must be a new group. Because they're identical components moving in the exact same way, it is okay to put them in the same group. The locked group in this case is the B side, and the force being applied is the ejector stroke of the press. Motion calculation where rounded parts have to slide by each other usually require a more refined time step. So in this case, I'll set the time span out to 6 seconds and get some extra calculations and accuracy. The free test of the motion is what I expected, and the design has no current interference, so that's good. An example like this might be one that needs a permanent connection or two to keep the parts from slipping around, but having the pins and some guided ejection included in the groups will do the job of keeping all the parts in line. So there should be nowhere for the smaller ejector system to go but up. Once again, the simulation ended with a collision warning. Showing only the parts involved illustrates that the tilting arms have hit the plate. I would not have known this for sure without actually putting the design into motion, So the couple minutes that it took to run this test was really worthwhile. Even with a stop due to collision, you still get to inspect the full motion analysis up to that point. So at least I know that the pin contact is going to work and the pin positions are okay. Don't be surprised if you see parts moving around on screen when you play the motion past the point of collision. This part of the grid was never calculated, so it has no meaning. Now let's look at a cylinder-driven pivoting mechanism. This design was well thought out, but it's a complicated system because multiple components all have to move at once. It would be nice to verify that the system won't bind up, but the only way to do this is with a real kinematic analysis of the parts. Remember the cardinal rule. Anything that moves independently has to be grouped separately. I can start with a group for the hydraulic cylinder, but for the motion to show the cylinder working, the rod has to belong to a different group. This means, of course, that the rod has to be drawn as a separate part in the assembly. The groups work on everything in one part at one time. Keep that in mind when you're creating the design. There isn't much else to say about grouping the parts that hasn't already been noted. Out of all the steps, this one does take the most time, but it's key to how the system analyzes the points of motion, so take care doing it. Keep in mind how your mechanism is designed to work and what parts are bolted together as one unit. For example, this mechanism has several bushings, and as I know that the outside of those is press fit, that dictates which of the groups they should belong to. You want the motion to behave just as the mechanism would on the shop floor. The group that's not moving in all of this is the last one, the mounting track. So that's the one that needs to be locked in place. The input force on the mechanism is the cylinder in motion, so that's a fairly easy vector to define. A free check of the motion looks like the cylinder working, so that's okay. And don't forget that open solids needs extra care when doing motion analysis. In this case, I know all of the parts are closed solids, so this won't be any concern. But an interference in the design is a big concern. This will stop the motion calculation before it even gets started, so it has to be fixed. The problem in this case is pretty simple. Some of these parts are standard components from step files, and the round on the cylinder pivot is colliding with the bushing block. I'll have to add a chamfer on the block to take care of the problem. Now the design checks out okay. With no initial interference problem, I should be good to go for calculation. Unfortunately, calculation doesn't get very far. the whole system seems to be in conflict. But the problem is actually with the definition of the input force. In this design, the cylinder has to tilt as the mechanism cycles. So this is a good example to look at because it shows how now I'll have to compromise a little bit to really get the motion analysis successfully working on all these moving parts. Instead of applying the force between two groups that are both in motion, I'm going to drive the design backwards by applying the force on the slide. And I think it might be best to calculate the motion in both directions to make sure there's no binding either up or down. Now that the system is pushing against the locked group, it's more able to calculate all of the resultant forces. This isn't an ideal situation, but the end movement is the same and it's still going to test the motion of the swing arm and the pivot, which is what I really wanted to accomplish here. The play controls include a repeat button to cycle through the result over and over. And there is also a speed adjustment factor if you want to slow it down some. Included in the motion analysis function is a way to record the playback. There are a few video codec choices in here, and I'm not really sure that every PC will support all of them. So you'll have to try them and see if it makes the movie okay to really find out which of these works for you. I'll end with displaying the checklist one last time. The fact is, motion analysis is one of the most powerful functions in the whole Cimatron product. The verification it makes is real. The playback tools are very nice, and really the whole function should be on your to-do list for design verification. Most definitely you do have to follow a few steps, but it's always well worth the time to try it. Make the groups correctly and don't overdefine the motions, and you'll surely get good results.